Okay, today we're doing 3.3 and 3.4. So in 3.1, we learned about real, distinct roots. When we got y1 was equal to e to the r1 of t, and y2 equal to e to the r2 of t. Today we're going to talk about complex roots and repeated roots. So distinguishing between general forms of solutions when the characteristic equation has distinct versus complex roots. So we still have our second order differential equation, and we know that the general form, or general solution, I guess I should say, general solution, is y of t is equal to c1 times y1 plus c2 times y2. And the r values, the roots, we need to find of the characteristic equation. Which is going to be a r squared plus br plus c is equal to 0. So this is how it works for homogeneous second order differential equations, linear differential equations. So we know we get a complex root when you get some kind of complex solution with lambda plus or minus mu I. So we'd say y1 of t is equal to e to the lambda plus mu I t, and y2 of t is equal to e to the lambda minus mu I t. All right, so this next part is Euler's formula and the explanation of how to use Euler's formula to get to this complex root. So some of us feel very interested in this and some of us will not. But Euler's formula, if we look at the fact that it has a theta I. So theta I, and what happens with the I and the theta. If we have e to the negative I theta, when we substitute in to negative theta and plus I sine negative theta, we're just plugging the coefficients into the formula. Cosine is an even function, so when I input a negative, the output is the same as when I had inputted a positive, versus sine being an odd function. When I input the negative, the sign is the opposite input. So opposite inputs yield opposite outputs. So we're going to have a negative in front of this one. So I would change this formula. Our y1 was e to the lambda plus mu I t. It's kind of like e to the lambda t times e to the positive mu I t. This part is real, and this doesn't require Euler's formula. But then this part is complex and will require the Euler's formula. So e to the lambda t, times cosine mu t plus I sine mu t. Then y2 of t is e to the lambda minus mu I t. So e to the lambda t times e to the negative mu I t. It's going to give me e to the lambda t times cosine mu t minus I sine mu t. So that's the part that plugged in. Blue is in Euler's formula. Yellow is not plugged in. Actually, you know what? I should have done not blue. Let's do green instead. Because that's this one. When we plug in the negative. Okay, so then when we do our general solution for this one, our general solution is going to be, actually, let's write it down here. Y of t is equal to C1 e to the lambda t cosine mu t plus I sine mu t plus C2 e to the lambda t cosine mu t minus I sine mu t. And then how do we simplify this? Because we're going to get something a lot easier to deal with. So if we add together our y1 and our y2, so we're just like kind of figuring out maybe what coefficients could make that happen. So if we added these together, you don't have to do this, but just imagine adding these together. Do you see how the I signs are going to cancel each other out? And so then you're left with y of t is equal to 2e to the lambda t cosine mu t. And really we only care about our coefficient. Each problem's coefficients are going to be different. So this part of the solution simplifies and really only deals with the functions operation. If it makes your heart feel happy, you could say like C1 is 1/2 and C2 is also 1/2, and that's how they could have made this happen. Oops. C1 this is like 2 or here, even better, I feel like C1 plus C2 will make you feel happier. And then if I subtract, so I'm doing y1 minus y2. So again, now if I take these, stack them on top of each other, and I think about subtracting, so I have a minus and a plus. How does that affect everything? The thing we're left with is the cosines canceling out and the sines are what's left. Oops, squeeze that I in there, mu t. So solving this one, because really the thing we care about is the function for our formula. So we're saying C1 is 1/2 I and C2 is negative 1/2 I. Okay, but really all of that is to prove our general form. So our general form is going to be yt equal to C1 e to the lambda t cosine mu t plus C2 e to the lambda t sine mu t. And there's no i's left in the problem. You can also factor out the e's. This is the general term. So the e should have the real number with it, and the trig function should have the same argument, and it should be whatever the complex number is. So this one goes with the real number, and this goes with the complex. Okay, so let's try to do 1. Our characteristic equation r squared minus 4r plus 9 equals 0. Okay, you can use your calculator or complete the square. Okay, so we get, this is lambda, this is mu. So our general solution is going to be y of t equals c1 e to the 2t cosine square root of 5t plus c2 e to the 2t sine square root of 5t. But we want to use these for the particular solution. Okay, so our initial condition, y at 0 equals 0. So 0 equals c1 e to the 0 cosine 0 plus c2 e to the 0 sine of 0. Sine of 0 is 0. So we get c1 is equal to 0. So already we have y equals c2 e to the 2t sine square root of 5t. So if I evaluated, and if I took the derivative first, then I'm going to have the product rule and it's going to be a mess. But me evaluating my initial condition first gives me only one setup of having to do the product rule, which is nice. Okay, so y prime is equal to 2c2 e to the 2t sine square root of 5t plus square root of 5 c2 e to the 2t cosine square root of 5t. Okay, and our initial condition was -8, or by condition, I guess. So we got -8 is equal to 2c2 e to the 0 sine of 0, so that's 0, plus square root of 5 c2 e to the 0 cosine of 0. So it gives us c2 is equal to -8 over the square root of 5. So y of t is equal to -8 over the square root of 5 e to the 2t sine square root of 5t. Okay, try to do example 2. You might need to pause. All right, our characteristic equation, r squared minus 8r plus 17. Don't just blindly follow me, because I'm skipping steps. So if you haven't figured out how to solve this by now, you're going to be confused. R equals 4 plus or minus I. Okay, using our initial conditions. I'm solving. Hopefully you've done this yourselves. Collaborate if you haven't. Now we're on 3.4. So 3.4, remember 3.1, we had y1 is equal to e to the r1t, and y2 is equal to e to the r2t. So that was essentially two real, or really, all of them are two because they're second order, real distinct roots. Then in 3.3, we just talked about having y of t equal to c1e to the lambda t cosine mu t plus c2 e to the lambda t sine mu t. And this was complex roots. Today, we're going to deal with repeated roots and reduction of order. So repeated roots is when we get having, like where it factors usually into a multiplicity of 2. And if you're doing the quadratic formula or completing the square, it's basically where the thing in the radical, the b squared minus 4ac, or whatever you square rooted when you like completed the square on both sides, is 0. So you're just left with the real part. So you really only would get one solution, but this is a second order linear differential equation, so there should be 2 solutions. So what happens is we have to do this reduction of order process. So you take a constant, and we're going to say some kind of function, v of t, becomes our y2. We take that, some function, and we multiply it by our known solution. So we're going to call it v is equal to negative 2at, because we're saying that's what y1 is. So remember, v is a function, not a constant. So when we take the derivatives and plug into our differential equation, we're going to need to do the product rule. Okay, so y2 prime of t is going to be v1 e to the negative b over 2a t minus b over 2a v e to the negative b over 2a t. This reduction of order is where a lot of simple mistakes are going to happen with our derivatives. And I'm going to teach you a trick at the end to make sure that you are doing your derivatives well. Plus b squared over 4a squared v e to the negative b over 2at. Okay, so this actually simplifies to be b double prime e to the negative b over 2at. Okay, and then those b's over 2a, there's 2 of them, so it's simplified to just be b over a, b prime e to the negative b over 2a t, plus b squared over 4a squared v e to the negative b over 2a t. Okay, and I kind of warp speeded that. Try to think about taking the derivative of yourself. And we're taking these 3 and we're substituting into the original differential equation. Okay, so we're going to have, maybe I should have done different colors here. a times plus b times first derivative v prime e to the negative b over 2a t minus b over 2a v e to the negative b over 2a t plus c times v e to the negative b over 2a t equals 0. Okay, I think we can see that we can factor out an e to the negative b over 2a t. And then if we distribute in the a to here, we're just going to have negative b v prime. And then if we distribute the b to here, we're going to have b v prime. So then those cancel each other out. And we have a v double prime. And then the constant, I think it would help if I did one more term. No e. Plus minus b squared over 2av plus cv. Okay, so then if we get common denominators here, I'm going to have minus b squared over 4av plus cv, which let's simplify that. Let's factor out the v, and maybe get common denominators. So this would be a 4a over 4a. So if I factor out the v from that second term, I have a v double prime. And then we'll say, factoring out the v, let's take out a negative 2 in the front. So negative v is going to be multiplying b squared minus 4ac. You know what? Let's also factor out. So b squared minus 4ac. Let's factor out the denominator that made them be common. That's interesting. B squared minus 4ac. The only reason we were doing this is because it was a repeated root, and that should be 0. I'm just saying, but you know, we'll find things out. Okay, so that's cutesy. We have v prime and v. We are trying to figure out what v of t is equal to. We know that v prime is equal to the integral of v double prime. And in this case, all of this stuff, our v prime should integrate to be some constant. So then v of t is the integral of v prime of t dt, which becomes some constant times t plus k. So y1 of t, it was equal to e to the negative b over 2a t. y2 of t, we said, was v of t times y1. which really is going to be ct plus k times e to the negative b over 2at. So let's plug it into the general form. Okay, think about what this is going to simplify to be. We're going to have C2ct plus C2k times e to the negative b over 2at and e to the negative b over 2at. Well, this term here is just a constant times e to the negative b over 2at, so this can be absorbed into here. And then we have, what's left over here is just a t times some constant. So the more simplified way to write this is going to be y of t is equal to c1 e to the negative b over 2at plus, this just becomes some constant. They get absorbed together. C2 t e to the negative b over 2at. So this t is all we needed to make it be different. So again, instead of doing the whole variation of parameters, reduction of order rather than variation of parameters, you just can you can just multiply by t. So let's see that in action. Okay, so our characteristic equation, r squared minus 4r plus 4 is equal to 0. This factors into r squared minus 2. So r is equal to 2. So all you have to do is y of t is equal to c1 e to the rt plus c2 t e to the r is 2t. Okay, so then in this situation, when I plug in my initial conditions, I'm not going to have anything that like cancels out right away. It's not equal to 0, first of all, so I'm just going to do my derivative first. 2c1 e to the 2t plus, we have to do product rule. C2 e to the 2t plus 2c2 t e to the 2t. So don't forget your product rule. All right, our initial condition. We got y at 0 equals 12. So 12 is equal to c1 e to the 0 plus c2 times 0 e to the 0. Makes c1 equal to 12. All right, my by condition. So we got negative 3. C1 was 12. E to the, times 2. Hang on. Just plug into the wrong thing. 2. C1 was 12. E to the 0 plus c2 e to the 0 plus 2 c2 times 0 e to the 0. 24 plus C2. So C2 is equal to negative 27. Plug those back in. Y of t is equal to 12 e to the 2t minus 27t e to the 2t. So repeated roots are actually pretty easy. It's an application of them with reduction of order that I think makes it really tricky. So reduction of order is the last thing we're gonna do today. And then I'm gonna show you how to simplify these. So in reduction of order, we need to assume the second solution is y2 is equal to some function times the initial solution. So if we make that assumption, we're saying y2 is equal to v times t to the negative 1, because here's our first solution. I'm going to take the derivative, product rule. Sure you realize it's v prime. It's not like a number, it is a function. Okay, I'm gonna simplify this. And plug these back into here. So as you might be able to see, lots and lots of places where some simple mistakes might happen. Minus 3. Okay. Simplifying. Sorry, I was doing my old way there for a second. Okay, so we got 2t v double prime minus 4 v prime, the t's cancel out, plus 4 v t to the negative 1, plus v prime minus v t to the negative 1 minus 3v t to the negative 1. Okay, looking through, things should cancel out. Let's see, or at least reduce. Do you see that this becomes negative 4v t to the negative 1, and we have a positive 4 t to the negative 1, so those cancel. And we have negative 4v prime plus v prime. So we have 2t v double prime minus 3 v prime equals 0. We are looking for a v satisfy this. So that means we need to solve another second order linear differential equations. But now we can just change the variable, which is just kind of like something cutesy that we're going to do. Change the variable. We're going to let u equal v prime. So that means u prime is equal to v double prime. So it's just a simple substitution that we're doing. So it means we have 2t u prime minus 3u equals 0. This is a first order diffeq. And it's separable. It's really you have 2t du dt, and then add the 3u on both sides. This is separable. So I'm going to divide by t and divide by u, multiply by dt. I also will bring the number with it too. Could have left it 2/3 on the left as well. So I was bringing the number with it. I wrote 3, not u. Okay, ln u is equal to 3 over 2 ln t plus c. Right, because like that's really where we could have integrated. Before I cancel out the ln's, I have to move this into the exponent. So I have ln u is equal to ln t to the 3 over 2. So then when I exponentiate both sides with e, this is now the exponent for e. So I have e to the ln t to the 3 over 2 times, because I'm adding the exponents, e to the c. We're going to make this e to the c just be a constant. Oops, and those cancel each other out to be c t to the 3 over 2. So v prime of t is equal to u of t, which was equal to c t to the 3 over 2. Well, we want a v. Well, v prime, we just said, v is equal to the integral of v prime. So v is equal to c, integral of c t to the 3 over 2 dt. So that means that v of t is equal to 2/5 c t to the 5/2 plus k. We really don't care about the constants. We only care about the function. So we would say v of t is equal to t to the 5/2. So then y2 was equal to v of t times y1 was t to the -1. So y2 was equal to t to the 5/2 times t to the -1. So our general solution, C1, y1 was t to the -1 plus C2, y2. Okay, dokie. Let's see if I have the solution written somewhere. That's going to take 10,000 years, though. So instead, do I have the answer just written somewhere? I don't. Okay, so we're going to skip down to me just explaining a little life hack for multiple levels of differential equation, and it's using Pascal's triangle. So if you notice, the second derivative becomes, if we have y equals f times g, then y prime would be f prime g plus f g prime. So it's like 1, 1. And then the second derivative of y is going to be, it's following Pascal's triangle. So this actually simplifies to be 1 f double prime g plus 2 f prime g prime plus f g double prime. So in Pascal's triangle, we make a triangle of 1, and then we add what's above it. All the sides are always 1. So then the third row is going to be 1, 3, 3, 1. The third derivative, we should be able to get f. Notice also, if we're saying f and g, that the level of derivative is always matching to whatever. If we add the level of derivative, it's whatever. There's like 2 primes. So the level of derivative on, if I want you to find the third derivative, should be matching. So we should have 1 f triple prime g plus 3 f double prime g prime. So now we have third derivative between the two of them, plus 3 f prime g double prime plus 1 f g triple prime. Okay, so finding the third derivative can be really frustrating. I like to make a little table for these. Okay, so if we're starting how it originally looks, cosine 3x. We're just taking the derivative of each of these respectively and not actually doing the product rule. So this would be 2 e to the 2x, and this would be -3 sine 3x. Second derivative would be 4 e to the 2x minus 9 cosine 3x. And we need to get down to the third derivative. 8 e to the 2x plus 27 sine 3x. Okay, so we're doing y triple prime should be equal to 1 f triple prime g no derivative plus 3 f second derivative g first derivative plus 3 f first derivative g second derivative, and then 1 f no derivative g third derivative. So we're going to get 1 8 e to the 2x no derivative for g is cosine 3x plus 3 second derivative of f was 4 e to the 2x first derivative -3 sine 3x plus 3. First derivative is f is 2e to the 2x. Second derivative of g is -9 cosine 3x plus 1. No derivative of f, e to the 2x. Third derivative of g, 27 cosine sine 3x. All right, I want you to try to do the fourth derivative. Try to pause so that you're not just copying me. Try to actually think in your own brain. So the level of derivative should always add up between the f and the g to whatever level of derivative we're trying to do. Okay, doing the fourth derivative, we got 16e to the 2x plus 81 cosine 3x. Okay, 16e to the 2x plus 4 times 8e to the 2x times -3 sine 3x plus 6 second derivative 4e -9 cosine 3x. First derivative of f, 2e to the 2x. Third derivative of g, 27 sine 3x. And honestly, while this seems like so annoying, think about how much more annoying it would be to actually have to do the fourth derivative with a product rule. So hopefully that helps you feel a little better. Okay, bye.